but I hadn't planned for there to be one, but because I realized last time I didn't do that and I thought maybe people wanted one.
It's okay. That's for lecture.
Okay, cool. That's fine then. So yeah, if you're new, well, welcome. It's really nice to have all of you here. And so today we're going to go over the optional winter review questions. I wonder if you have had a chance to either have a go at them before or or have a look at least. But yeah, I'll try and share something. So the plan for today is, Rachel, I think it says I can't.
Oh, I need to make you the co-host. That's right. Sorry.
That's okay. But yeah, in the meantime, I'll just walk you through what we're going through today. So,
Great.
oh, awesome. Okay. Yay. So, do you see like a whiteboard or something at the moment? Okay, great. Yes. So the plan for today, the topics are like in the review session. It's in the PDF, it's divided kind of based on binary and then the maths and then the quantum stuff. But I thought we'd do it slightly differently so that you can kind of refer to lectures and it's divided topic wise. So I thought we'd go over, so the main topics are we've got binary, we've got statistics, and then we've got the really big ones, so vectors, complex numbers, and matrices. And if at any point, should you have any questions, obviously leave them in the chat and I'll try my best to get to as many of them as possible. And so, yeah, I wonder if people have a preference on which topic we should start on. Does anybody have any preference? Okay. Doesn't look like anything's in the chat at the minute, so that's fine. We can just go through the questions. So, okay, let's go through the first question then. The very first question is a binary question. And the first question says, to convert the binary numbers to decimal. And I'll go through the last one. So we've got 1, 1, 0, 0, and 1. And I do apologize for my rather poor handwriting, but I'm trying my best here. So the way you convert this to decimal is you look at the place values. So normally in binary, in decimal value, we have like place values and you increase by 10 every time you go to the left, and you kind of divide by 10 every time you go to the right. And so in base 2, which is binary, we just do the same exact thing, but with a number 2. So we're timesing by 2 every time we go to the left, like that. And so we start off with this one being 2 to the 0, which is 1. And then we have 2, which is 2 squared, 4, 8, and then 16. That's a wonky 6. But you basically just add all of these numbers. So you times 16 by 1, and you get 16. And then you times 8 by 1, you get 8. And then you times 4 by 0, you get nothing, 0. And the same for 2, and then 1 times 1 is 1. So if we do the multiplication, if we write it out, this would be 16 plus 8, because we had that, plus 1. And then that is 24 plus 1, which is 25. So that's how you do that. And if you were to go the other way, so let's go through question number 2 then, because that goes the opposite way. So number 2, let's take 127. So here we have 127, and we want to convert this into base 2, so something like that in that form. The way we do this is, again, the easiest way to do this is to write out your place values. So you can start either way. Let's start from the left. So we've got 1, which is 2 to the power of 0. Then 2 to the power of 1 is just 2. And then we have 1, 2, 2 to the power of 2, which is 4, 2 cubed, which is 8, 2 to the 4, which is 16, 32, you just times by 2 each time, 64, and then finally we have 128, so this is 8-bit binary, and we're looking for 127. Now, if we wanted to make 127, we don't need 128 because that's too many. So we need a 64, we need a 32, we need a 16, we need an 8, we need a 4, we need a 2, and we need a 1. And if you added all of these numbers up, so 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you get 127, which is what we want. And normally, if the question hadn't specified this, but if it says, write your answers in 8-bit binary, you'd need to put the little 0 here to say that there's 0 lots of 128, 1 lot of 164, 32, and so on. So yeah, so the answers in the PDF, I had a look, and it omits the leading 0. So your answer would just be 1111 111 7 times. So that's how you go back the other way. So that's that. And now if you were to do addition in binary, and by the way, this is like one of the very first things that we learned. So if like, yeah, if you feel like you've forgotten, it's completely fine. But yeah, okay, let's do some addition now. So let's go to number 3. Number 3, I think, is 1 1 1 0 0, and then we have 0 1 0 0. Oh my god, my handwriting has gone so poor. Okay, so we're trying to add these two numbers, and like if you remember from when you learned normal addition, when you were like really little, you kind of write it out like this, and then you just go digit by digit. So that's exactly what we're doing here. So 0 plus 1 is just 1. 0 plus 0 is 0. 1 plus 0 is just 1. So anything after 0 is 0. Now, 1 plus 1 is normally 2. But 2 in binary is written as 1 0. Because if you just, let's see if I can switch colors. Okay, so this, every time you're converting between binary and decimal, it really helps to just write this out, because this is not like, if it was base 10, you could just do, 10, 1, 10, 100, 1000, and so on, and you're happy, you can do that in your head, you're comfortable with it. The base 2, you just want to get used to it a little bit more, so just always write this out. And so we can see that 2 would be written as 1 0, because we want the 2. We don't want any of these numbers because they're too big. And then we have a 0 because we already have 2 exactly. So going back to our addition, we have 1 plus 1 is 2. But remember, in normal addition, so when you do it kind of in base 10, you carry numbers over. And that's exactly what you do here. So you write the 0 and you carry over this 1. So that goes kind of there. And then again, you have a 1 and a 1 again. So 1 plus 1 is 2 again, and 2 in binary is 0 and 1. So this is your final answer, 1 0 0 1 0 1. And if you were ever unsure, you could always turn these numbers back into decimal or denary, perform the addition as normal, and then convert your answer back to binary. That's a bit of a long-winded way, I suppose, of doing it, but it is a way to check your answers. Also, you will never have to do this. You could always use a calculator, but it's really good to know how these bits work. Yes, so I think to summarize this bit of the question, if you had 0 plus 0, that's always 0. 0 plus 1 is 1. 1 plus 0 is also 1. And then 1 plus 1 is 2, so which is 1 0. And then if you had, say, if you had 1 1 1, so that's 1 plus 1 plus 1 is 3. 3 in binary would be 2 plus 1, so we write 1 1. So that is all for this question.
Nitya, just so you know, I asked folks in the chat, so thanks for responding. Many students who are on the call today are new students who just joined at the start of first semester. So, or sorry, at the start of second semester. So this review is probably very helpful.
Okay.
But just so you have that context.
Okay, that's really good to see so many of you guys here. I guess I should have done a little introduction then, but it's all right. My name's Nitya, guys. I'm a first year undergraduate student. I'm studying computer science, so this stuff basically. But yeah, that's me. And yeah, if there are any questions at any point, just please let me know. If you feel comfortable using your mic, you can get my attention using your microphone. If not, just put it in the chat and I'll try my best to keep an eye out.
Yeah, they're a little bit more informal than lab. So this is the time to be engaged and ask your questions if you have specific ones.
Yeah, absolutely. Cool. So I didn't see any questions about this, so hopefully it's all good. I'll give you like 2 seconds if you want to get a screenshot. This rather messy board. Okay. Someone says they've just joined. You have missed question 1, 2, and 3, which was just binary. This is all the stuff that we've done. So I'm going to take a quick look and see if you're happy with that. Yes, I am. Thank you. Okay, good. Great. Okay, then moving on to question 4. We have, this question was to draw out, oh, hang on, let me just bring up my questions. Let's see. Whoops. I think this was to draw out the truth table and then the logic gate. Somebody asked where the homework is. It is, you can access it via Canvas. It's under the title of optional winter review questions, I think. If you can have a look there, that would be great. Okay, so question 4A says, draw out a the truth table and logic gate for not A and B. So let's do the logic gate first. So we have this bit A, and it's going through our NOT gate, which is this little triangle with a circle. And then we have that. And then this is not A. So this is, this is not A. And then we have B. And then we're ANDing both of these. So we're putting them through an AND gate. Symbol for an AND gate is this massive D. That's how I remember it anyway. So we have a NOT gate and an AND gate, and then we have the output. So this is what the logic gate looks like. And then if we do our truth table, so we have A and B, 0, 0, 1, 1, 0, 1, 0, 1, and then we have the output. So remember, the reason we have 4 states essentially to consider is because we have 2 bits. So not 0 is because we're putting A through a NOT gate. Actually, why don't I do a little, let's do this on the side. So this is not A. That's a mathematical or like computational, I guess, symbol for not. So not A, so not 0 is 1, not 0 is 1, not 1 is 0, and then not 1 is 0 again. So the output of not A, which is this column right over here, and then B is, well, what is 1 and 0? That would be 0. 1 and a 1 would be a 1. 0 and 0 would be 0. And then 1 and 0 would be 0. So this is the output, and this is the truth table for the logic gate that we've drawn above. So that is it for question 4. We have a bunch of other gates as well. There's the OR gate, which looks like that. There's the exclusive OR gate, which is the OR gate, but with a little line through it in the front like that. What else? What else do we have? Yeah, these are the gates. So these are like the basic gates that you need to know. And these are classical gates, by the way, if anybody's wondering. And then we have quantum gates, which is they were going to look at this semester in a lot of detail. So that is to come, which is exciting. But other than that, if there's no questions on this one, we can move on to the next topic. So we've just done all of the binary and the logic gates and things. So okay, I think everybody's happy. I don't see anything in the chat. Okay, we can move on then. So let's jump now to question number 20, which is one of the statistics questions. So question 20 says, let x and y be independent discrete random variables. Okay, and they can be one of the values 1, 3, 4, and 7. The probability of x and y is different, and that's given in the table. It would be helpful if you had the question that I'm reading along, just so you can kind of see what I'm actually talking about. And we asked to find the expectation and variance of x. So for this question, we find the expectation. Now the expectation is another way to say the mean value. So the mean value, which is the expectation, is written as E of x. So this is the expectation of our discrete random variable x. And the way we find this is we times the probability with what x can actually be. So we have 0.2 times 1, which is just 0.2, plus 0.3 times 3. And then we have plus 0.15 times 4. So we're just timesing the probabilities by the actual value that x could be, plus, and finally 0.35 times 7. And so if you were to just do the multiplications, put this in your calculator, and that's all this is. Oh, sorry, this is question 20. You would get 4.15. So that is the expectation of x. And the second question asks for the expectation of y, but it's the exact same process. So if you haven't done the homework already, I would recommend you go through that. And then we can look at the variance of x. Now the variance just tells you how far away it is from the mean. So how far away your values are from the mean. So that's normally written as, that's abbreviated to be like var of x. And this is E, which is expectation of x squared, take away the expectation, which is what we had found in the previous part, which was this 4.15 squared. Now this can look a bit confusing, so let's take this step by step. So first of all, we have E of x squared. And what this means is we had the different x's, so we had 1, 3, 4, and 7, and we're squaring each of them and then finding the expectation. So in this case, we would have 0.2 times 1 squared is just 1, so I'll just leave that out for now. And then we have 0.3, but remember, we're not timesing by x anymore, because if we were to times by x, we'd take 3, but we're timesing by x squared, so we need 3 squared, which is 9. And then we have 0.15. So the probability does not change. So don't square the probabilities, just square the x, because we're trying to find the expectation of x squared. So you can think of these numbers as like 9, 15, 9, 16, and 49, and that would be like x squared. So you can just think of it as like a different problem altogether, but you're doing the exact same process. So that would be 4 squared, and then 0.35 times 7 squared, which is 49. And so if you do this multiplication, you get this term, which is e of x squared. And I've done the multiplication before the session, and that works out to be 22.45. Okay. And then we have the e of x squared, so the expectation squared. It can be really confusing to just say, because both of them sound pretty much the same. But anyway, we're trying to square 4.15, and so therefore the variance of x is then this bit that we literally just found, which was 22.45, and then take away 4.15 squared. And again, you can just plug this in your calculator. You don't have to do it by hand, and you get 5.23 to 3 significant figures. So this is the variance of x. So this is how you'd work out what the expectation variance of x is. So is everybody happy with that? And just leave that on for 2 seconds. Okay, I don't see. Great. Okay. Okay, good. People understand. Okay, awesome. So I can get rid of that then. Next, we look at question 28, because it's kind of like the same area of maths. So just wanted to get it all done together rather than go in the exact order of the questions. I hope that doesn't confuse you. But question 28 says we have a state phi, and it is √3/5 times the 0 ket, and then √2/5 e to the I pi/2 1 ket. And what is the probability that we measure the state 1? So this has a bit of, I guess, jargon, because it looks different. So we have, first of all, we have this weird notation. This is known as Dirac notation. So yeah, this notation, so anything inside the you put, it could be anything, means it's a column vector. So you have whatever, any number of any dimensions, it's a column vector. So this is used to commonly represent a qubit state, and that is equal to square root 3/5 state 0. And if you haven't seen this before, this is probably going to be helpful. So as I said, anything so this little pair of lines, I suppose, is known as a ket, and it's a column vector. So this is read as the 0 ket. And I always get this the wrong way around. The 0 ket is 1, 0, okay? And then the 1 ket, or alternatively state 1, is 0, 1. So anyway, going back to our question, we have a state which is phi, okay? That's what that Greek letter is. And then it has √3/5 plus √2/5 e to the I pi/2 1. Okay, and we're asked to find what the probability of finding this state in the state 1 is, purely. And the way we do this is we square the terms here. So the terms here are what's known as the probability amplitudes. And if we wanted to work out what the probability of these states 0 and 1 is, what we do is we square the probabilities. So, and the reason for that is because sometimes these amplitudes, these probability amplitudes can be negative and all sorts of things. And there's one basic rule in probability, and that is that probabilities are always between 0 and 1. And so you cannot have a negative probability. So we square them just to get rid of all of that. So the probability of finding this state in state 1 is just square root 2 over 5, all squared. And that is equal to 2/5. So that was all we had for statistics and probability that I wanted to go through. Is everybody happy with this sort of stuff? Okay, people say yes. Thank you, Isabella, for getting back. Right, okay. So I'm assuming everybody's happy with that. We can then move on to the more exciting topics and the larger topics. So then we'll move on to vectors. So vectors, let's look at question number 8 first. So we have a boat and it travels north with a speed of 20 knots. That's just a measure of speed, like meters per second. It could have been anything. But yeah, here it's 20 knots. And there is a wind blowing from northwest to southeast that has a magnitude of 5√2. What is the resulting velocity of the boat? State both the magnitude and the direction of the resulting velocity. So there's several things that's what it's trying to say here. And first of all, there's a boat, which I'm not going to attempt to draw. We're just going to model it with this little dot. The first thing to do in like questions like this is if you draw yourself a really good diagram, then that's basically all you need, because it makes life so much easier. So we have a little boat. It doesn't matter that it's not a real boat, but yeah, it's going. So just so we're all on the same page. These are the directions I'm going to be looking at. So the boat is going north with a speed of 20 knots. And then there's a wind, which is blowing from the northwest, so here, to southeast. So sort of like that. And we go kind of like there. And it's 5√2. And we're asked to work out how much the boat kind of goes off its path and what speed it finally has. So this can look like a really tricky question, and you might be tempted to try Pythagoras, but what you have to remember is that there's no right angle triangles. So the resultant of these two vectors, and remember, a vector is just something that has a magnitude and direction. So the resultant of these two vectors is going to be like somewhere like that, maybe. So you imagine you're going straight and then you feel like a really strong wind from your left. You're going to kind of walk towards the right. So that's what's happening to the boat as well. And we're trying to work out what the angle is with respect to like the x-axis. And we're trying to work out what the speed is, which is the magnitude of this velocity. So this velocity composes of the speed and then also the direction. So the first thing that I want to do is I notice that the boat is exactly on the y-axis, and that makes my life a lot easier because I don't need to do anything. It's already in one of my kind of perpendicular rectangular components. But the 5√2 is not. And I want to make this so that I want to split this vector into its component form. So it's going to have, it's going to have an x component, and it's also going to have a y component. So like that. And then you can see how this would be the resultant of both of these vectors. Now, the x component of this vector would be 5√2 That's because that's what this diagonal is, over root 2. And then the y component would be also 5 root 2 over root 2. Okay, so that's just 5, which is very nice because it simplifies our equation. And now we have to think, because we have this vector and this vector. And now we just look at the two vectors in the same direction. So that's gone quite messy. So let me try doing that again. So now if we look at the x direction, so we're trying to find the final velocity of the boat, which the question gave us a variable v. And if we look at the x, we have a certain speed in the x direction, which we worked out to be was 5. So we put that in. And then always look at the x and y as separate directions. They have nothing to do with each other. It doesn't matter that the wind is going from northwest to southeast. We just want to look at the x and y. If we do that, then you simplify your life a lot more. So on the y-axis, we have something really interesting going on. We have 20. The boat is going at a speed of 20 upwards or forwards, and there's a wind, but it's pushing it backwards exactly by 5. So these vectors are going in opposite directions. So when you add them, you have 20 plus minus 5 because it's in the opposite direction. And so 20 minus 5 is just 15. So we have 15. So this is the vector, but we're not quite done because we need a magnitude and we need a direction. So, and the reason I chose this particular question, number 8, to go through is because this kind of ties together all of the vectors concepts that we've done so far in the course and the concept that we'll need. So I thought this tied everything together really nicely. But yeah, so to find the magnitude of this vector, those two little lines just mean we're trying to find the magnitude, and we do that simply by taking the square root of the x component squared and then the y component squared. Oh, that's a 15. And then this is, what is that? 25 plus 2, 25. And then, what is that, like 350? And then that is 5 root 10. So, so this is the magnitude. And so we found one part of the question, which was to find what speed it's going at in the end, which is that. And we want to work out what the angle is. Now, the angle of this green arrow, which is what we're trying to find, would be the inverse tan. So that's not tan to the -1, that's inverse tan. So it's not 1 over tan, that's a different thing. Trigonometric functions, this is like a weird thing that you have to just get used to. So inverse tan of 15, because we have the y, so essentially we have, rather than having it all the way up to 20, we now, as a result of this wind, we're only at 15, something like that maybe. And then y over x, so inverse tan of 15 over 5, which is just inverse tan of 3, which I have done in my calculator before the session, and it works out to be 1.25 radians to 3 significant figures. So this is the final answer for the direction, because now we've said it's going 1.25 radians and it's going at this speed of 5 root 10 knots. So this is the final answer, and that's how you do this question. Does anybody have any other questions on this? I think it's all good. If everybody's happy, we'll move on to question 24. And this is a bit of a weird one because it combines vectors and also complex numbers. So we're given the a ket is, or state A is 4, and then minus 3e to the minus I pi over 4. And what is bra of A? So let me clear that. Question 24. So we're given A is 4 negative 3e to the negative I pi over 4. And we're asked to find the bra of A. So if you haven't seen this notation before, it can be a bit confusing, but it's actually really nice. This is known as the bra ket notation, and it's sometimes also known as the Dirac notation, named after the physicist Paul Dirac. So we discussed the kets earlier, which is a column vector. A bra is a row vector. So if you have, I don't know, anything of this form, it's a row vector. And if you have anything of that form, it's a column vector. So the way you find a bra from a ket is you take what's known as the conjugate transpose. So a normal transpose, again, this also starts to bring in some matrices. So the idea of a transpose is that you take a row vector and convert it into a column vector, or if you have a column vector, you convert that into a row vector. So we're doing the latter in this case. And then we have 4 minus 3e to the minus I pi over 4. And now if you want to take the transpose of it, we first of all we have 4 as the first element, and then rather than having a column, we have a row. So the next element would be negative 3e, but remember it's not just a normal transpose because we have this complex term here. This is a complex number, so we can't just take the normal transpose, we have to take what's known as the conjugate of this as well. So the conjugate of a complex number, again, this is bringing in a different topic, this is complex numbers. So the conjugate of a complex number when it's written in this form with e and e raised to the I some theta, so in this case it's pi over 4, you just flip the sign. So rather than having negative 3e to the negative I pi over 4, you just have negative 3e to the I pi over 4. And this is your bra. So this is the conjugate transpose of this state. So hopefully that made sense. Is there anything that people would like me to clarify? How did I get square root 5 square root 10 in the previous question? I just plugged it in my calculator. So if you just do the maths for it, you plug in your calculator, that should give you an answer. But you could also just do it by hand. I hope that helps. Okay, so is everybody happy with bra ket notation and conjugate transpose? I think there would be other questions that would kind of consolidate this for you. So if that's all good, then we can move on. Okay, people say yes. Okay, awesome. So let's move on to complex numbers then, because we're doing complex numbers now. So I'm looking next at question number 9. So question number 9 says, express the following complex numbers in polar form using Euler's formula and express your angles in radians. So polar form and Euler's formula. So 4 plus 2i is the question. Okay, let me, number 9. So we have 4 plus 2i. Now Euler's formula, if you haven't seen it before, it's another way of expressing a complex number. So a complex number is made up of a real part, which is a in this case, and an imaginary part, which is the IB. And I is the imaginary number, which is the square root of negative 1. And an alternative form to express this complex number, let's call it Z, is to write it in terms of R, which is the magnitude, E, which is Euler's number, to the I, which is the imaginary number, and then theta. So this is the polar form because we have R and theta. Just a quick side note on polar coordinates. We have, so you know how we have like the normal way of representing the point. We go certain direction in X, maybe that's 1, maybe that's 1. And then we have 1, 1 to describe this point. There's another way, it turns out, to describe numbers, and that is using polar coordinates. So rather than using X and Y coordinates, we have what's known as a pole, which is fixed. So that's fixed at 0. And then it's like going in circles around the pole. So let's say you want to talk about this point. In order to describe this point, you need an R and a theta. The R is the distance from the middle of the pole, just that. And the theta is just the angle from the x-axis in the anti-clockwise direction. So that's what these R and theta are. So the question is, we want to express 4 plus 2i, which is currently in this form, where a is 4 and b is 2 and I is just I. And we want to take it to this form. So this is the Euler's form, okay? And the way we do this is, first of all, we want to work out the magnitude. And again, this is where also brings in vectors, because you can express this 4 plus 2i as a vector. So how would you do that? Well, you have 4 on the real axis. This is no longer x and y, don't be confused. So you go 4 on the real axis, and then we have 2 on the imaginary axis. And so we have a vector. And so look, this looks awfully similar to this diagram here. So we have this vector, we want R and we want theta. And how do we do that? Well, we first of all try to find the magnitude. So R, again, how would you do it for vectors? Exactly the same as we've done in the previous question. So you do 4 squared and then 2 squared. Okay. That is 4 squared is 16, 2 squared is 4. That is square root of 20, which is 2 root 5. Okay. And then we want to, so this is the magnitude. Okay, so the final goal is to get this in the form of this. So we found R, so we're halfway there. And then we just want to, work out what the angle is. Again, if this was a vector, what would you do? Inverse tan, just like before, which is why I said all of these topics are really interlinked. So it's like really nice consolidation. So again, just think of this as a vector. You know, you could even write it like a vector. That's also allowed. And then we do 2 over 4, which is inverse tan of half. Again, I've done that in my calculator beforehand, and that works out to be 0.464 radians to 3 significant figures. One little thing to remember in both examples, we came across inverse tan in the first quadrant. It's not always going to be in the first quadrant, so it's a good idea to draw it out and see on which quadrant the angle is going to lie. Because sometimes, you know, your vector could be like there, and then you work out this entire angle. There's a question: is the inverse tan in degrees or radians? So I've done this in radians. That's usually a good measure, because degrees is a bit arbitrary. It's a bit random in that, well, what does degrees mean? Who decided a circle should have 360 degrees, right? Whereas radians has a form of mathematical definition, and so we always try and stick to radians. But you could do this in degrees. If you did this in degrees, I don't know what the answer would be, but yeah, if you just changed like the output mode in your calculator from radians to degrees, you should get inverse tan of 2 over 4 in degrees as a different answer to this. So I hope that answers your question. It does look like there's any more questions. So I'm assuming people are happy to move on. The next question that I wanted to look at was number 14. So, okay, I didn't see any questions, so we'll look at number 14. So here we're asked to find the inner product, and I'm going to look at 14C, just so we get comfortable with using complex numbers. So we have 3 and minus 4i. See, I didn't know how to separate the topics because, like, is this complex numbers or vectors? I guess it's both. But anyway, so we have both of these vectors, and we're trying to find the inner product. So the inner product is also like sometimes known as the dot product, and it gives you a scalar value. So these are vectors, which means they have a magnitude and direction, but a scalar only has a magnitude. And so what this inner product does is it takes two vectors and gives out just a number. So the way we go about doing this question is, first of all, you can't just multiply both of these vectors just like that, because yeah, I'll talk about dimensions very briefly. So vectors and also matrices have something known as a dimension associated with it, or a size, or like sometimes called shape as well. And the shape or size or dimension is the number of rows. In this case, it's 2, so we have 2 rows, and then 1 column, 2 by 1. And let's say we had another vector, but let's say this time it's a row vector. We had just one row, but then we have 2 columns, so 1x2. So if you wanted to like ever multiply matrices or vectors, they always have to, like, the inner number has to be the same. So always just remember that. So if you had something like if you had, I don't know, A, B, C, D. So this is a 2 by 2. And let's say you had, let's take AB again, but this is just this, and that's 2 by 1. In this case, you cannot multiply these together. Oh, that looks bad. Wait, there we go. 2 by 1. In this case, you can't multiply these together because, like, the inner numbers don't agree. So that was a little brief talk about dimensions, and you see that we can't really times these together. So what we do is, well, we find, this is normally, like, if I call this A and if I call this B, the inner product is normally written as that in bracket notation. And so we'd have to sort of actually, no, I don't want to confuse you. Basically, just get this as a row vector and as a column vector, 3, 5. And then what you do is you multiply each element. So this is the first element. You times that by the first number. So 3 times -3 is -9. And then you take the second number and times that by the second number. So this is a row, that's a column. Oh, sorry. And then you times both of these together. So we have -4i times 5i. So -4 times 5 is just -20. And then I squared is -1. So we have 20. And oh my God, sorry. I just said you get a scalar and then I started doing a vector. So you're supposed to add these. I'm so sorry. And then when you add this, you get 11. So yeah, okay. I hope that didn't confuse you. Is that okay? Should I walk through that once again? Yes, of course I can repeat that. Shouldn't the first vector be a complex conjugate? No, because we're not, so this is not bracket notation. This is just, we're just trying to find the inner product. So when we're trying to find the inner product, you don't have to take the complex conjugate of it. You just, hang on, no. What am I talking about? Yes, sorry, of course you need to take the complex conjugate. Oh my God, I'm very, very sorry. Yeah, so that should indeed be positive. Oh my goodness me, I feel terrible. Okay, we're gonna walk through this again, okay, and we're gonna do it right this time. So, okay, let's start from scratch. So we have two vectors and we're trying to take the inner product, and we discussed they have to be kind of the same dimension, and so we take the complex conjugate. Thank you, Samichi. I'm sorry if I mispronounced that, but I completely missed that. So you take the complex conjugate, you're absolutely right. So 3 just says 3 because it's real, and then 4i becomes positive because we're taking the complex conjugate of it. And so we've done the transpose, and then we're timesing that by the column vector, which we haven't changed. And so that's -3 and 5i. So that's just a column vector as it is. And then what you do is you times the first element of your first vector by the first element of the second vector. So that is 3 times -3, okay? And then you add, it's not going to be a vector, it's going to be a single number. You add that with 4i times 5i. So 4i times 5i. And then 3 times -3 is -9, plus 4 times 5 is 20, but I squared is -1. So that's going to be -20. So that is -20 minus 9, which is -29. Okay, so is this better? I'm so sorry about the mistake I made earlier, but this, I believe, is correct now. So do people understand? Okay, good stuff. Okay, great. Yeah, I do apologize. Okay, the next question that we're going to go through is number 15. Could I do another example with a bigger matrix? Yes, I can. We're going to see that in just a moment after this question. So if I just get done with vectors, and we're going to move on to matrices, and there's going to be examples there. So I hope you could just hang on for a couple of minutes and then we'll get to that. Right, so question 15 says, consider the vectors A is -2, 5, and B is 1, 4. And then we're trying to find a linear combination of A and B to form the vector -1 and 9. So we had A. A was, what was A? Was it -2, 5? And then we had B. Ooh. Always remember to put the little arrow at the top because that means this is a vector. We had 1, 4. And then we're trying to find a combination of A and B. So some number X times A plus a different number Y times B, the vector B. So X and Y notice are just scalars, which is why they don't have that little, that should be an arrow, guys. Sorry about that. To get the vector, what vector are we looking for? -1 and 9. So the way we go about this is quite like, there's an algebraic way to do it, so we'll do it that way. So as I said, we had X and then -2 and 5 because that's what A was, so X times A, so I'm just plugging things in here, plus y times b, which is 1, 4. And that is equal to negative 1, 9. All right. Now, what we do here is something rather nice, actually. So we have like an x and we have a y. So we collect the x terms together. So the x, I guess it's a bit confusing because I used x and y as my actual variables. But when I say x component and y component, I'm just talking about -2 being along the x-axis, 5 being along the y-axis. Same thing with 1 and 4, 1 being along the positive x and 4 being along the positive y, and so on. So we collate, basically, we collect the x and y terms together and we separate them out and then we equate that. So that was quite a lot of words. So let me show you what I mean. So we mean collect the x terms, so times x with -2, -2x, and then plus we collect all of the x terms. So y times 1 is also an x term, so that's just y is equal to -1 because that's that. So notice it's kind of like the top, the top row. And then we do the same thing for the y terms. So we had x times 5 is 5x, and then plus 4y is equal to 9. So now we have 2 equations and 2 variables, and we can solve for this. So you can either do this by hand or use a calculator, but it turns out that the answers, so the numbers that satisfy x and y that also satisfy both of these equations is x equals, oh, I got the wrong color. Is x equals 1 and y equals 1. And so that is your answer. So the linear combination of 1 times -2, 5 plus just 1 again times 1, 4 gives you -1, 9. Now I am very aware that like you could have just kind of guessed and checked that -2 plus 1 does indeed equal -1 and 5 plus 4 equals 9. But I just wanted to show you like an algebraic way of doing it if trial and error doesn't always work. So that is your answer for this. So how is that looking? Is that okay? So this is the final question that I had, and oh, I guess this wasn't quite complex numbers, but yeah. Okay. If people are happy with this, we can move on to matrices. Okay, awesome. Nice. So matrices. I'm next looking at question number 16. Calculate the conjugate transpose of each of the following matrices. So I'm looking at 16A. Let's see. Oh, have I missed anything in the chat? Okay, great. Okay, so 16. 2, no, that's -2. 3 plus I, oh my goodness, what was that? 3 plus I, 1 minus I, and -4. So we're trying to find the conjugate transpose of this matrix. Notice this is a 2 by 2 matrix, and when you take the conjugate transpose, you will still get to a 2 by 2 matrix. And the symbol for a conjugate transpose is known as a dagger, and it's represented by that. And the reason we're taking a conjugate transpose as opposed to a normal transpose is because we have 2 complex terms here. If you were to take a normal transpose, then the symbol for that is just the English letter T. I think sometimes it's also represented by like a little dash. If you had a matrix, and that dash could mean a transpose, but that's just notation. You don't have to worry about that. So now that we've talked about conjugate transpose, could people help me with this? So what could people say what the first term would be? And feel free to use your mics if you want, or you could pop that in the chat. So what would the first term of my new conjugate transposed matrix be? 2. Oh, 2? You sure it's supposed to be, you don't flip the sign if it's a real number. So if it's a real number, then the transpose, you don't have to conjugate it. Conjugation is only for complex numbers. So yeah, there's another answer in the chat, and it is indeed -2. Yes, you only conjugate the imaginary part. Yes, that is right. Okay, so then what would be the next term? 1 plus I, 1 minus I. Okay, I see 2 answers. So again, as people correctly said in the chat, you only conjugate the imaginary part, and so that would mean you negate the sign of the complex bit. So the complex part here is I, and it was negative I, so that's positive I. So that's that. All right, what would this term here be? Three minus I, perfect. Okay, thank you for your answers, by the way. 3 minus I, and the final term is -4. Great. So that is it. This is how you do a conjugate transpose. So yeah, lots of good answers coming in. Very good. Yeah, so that's what you do for this question. So that was nice and simple to start us off with matrices. Next, I'm looking at number 17, and the question asks for the inverse of the matrix. So, oh my God, I've lost my screen. Sorry, bear with me a moment. Okay, there we go. Wait, you can still see my screen, right?
Yes, we can.
Okay, great. Sorry, yeah, something had happened. Right, we go through the inverse of this matrix. So we have -2, 1, 3, and 2. And the inverse is represented with this little -1 here. So we're trying to find the inverse. And when you take the inverse of a matrix, what it just means is that when you times it by the original matrix, you get what's known as the identity matrix. And in this case, the identity matrix, because we're in 2 dimensions, the identity matrix is the matrix which looks like this. So it has 1s on the leading diagonal, which is this diagonal, and then 0s everywhere else. So if it was 3 by 3, it would be 1, 1, 1, and then 0s everywhere else. So that's the identity matrix. And when you take an inverse and times it by the original matrix, you just end up with the identity. The way you do the inverse is you find the determinant of this matrix, and that's just like a fancy way to say, actually, let me do this. Let's take a generic matrix, right? A, B, C, D. And we're trying to find the inverse of it. So the determinant of this matrix is AD. So you times across. So A times D, take away B times C. So this is the determinant of the matrix. So the determinant of this matrix would be 2, -2 times 2. So that is -4. And then subtract 3 times 1, which is just 3. And that would be -7. So yeah, good answers in the chat as well. Very good. So that is the determinant of this matrix. And to find the inverse, so that is the determinant as well. And then to find the inverse, what you do is you do 1 over the determinant. And then for 2 by 2 matrices, there's a nice little trick where you swap these 2 elements. So you swap A and D. So D goes to A and A goes to D, and then it should be -B and -C. So you negate these terms and you swap these terms. So the inverse for this question then would be 1 over the determinant, so -1/7, which is 1 over the determinant, and then times, that is times, 2, -2, -3, and -1. And this is it. This is how you find inverses for 2x2 matrices. There are methods to do inverses of 3x3 matrices, but that is a really, really long process. And quite honestly, you don't need to know how to do that. But if you ever need to do 3x3 matrices, you could always use a calculator. But for this course and for like the purposes of this course, that is like an unnecessary complication. There's a question, is it 1 over the determinant or -1 over the determinant? It is 1 over the determinant, but since we had a negative determinant, I just wanted to make it look nicer, and I just put the -1 at the top. But yeah, it equally could have just been 1 over -7. The convention is normally to write the negative, to not have a negative in the denominator, which is why I have gotten that. So I apologize if that confused you, but yes, it is 1 over determinant. Okay, so that was all for question 17. That's okay. Welcome. Don't see other questions, so we can move on. I am mindful of time. Right, 29. Okay, let's go to question 29. So clear all drawings. Next, I'm looking at question 29, which is where we get to some of the quantum stuff. So using matrix multiplication, calculate the following H. So I'm looking at, I don't know, what should we do? Let's do part G. I like G. G looks good. H0. So let's see. 29. We're trying to do matrix vector multiplication. Remember, now H is what's known as the Hadamard gate, and this is a quantum gate. Remember, like the very start of the session, we looked at what was it, like AND gate, OR gate, and classical gate. H is known as Hadamard gate, as I said, and it's a quantum gate. And in quantum computation, we represent these gates as matrices, which is why we looked at so much matrices, and they can have complex numbers as well, which is why we looked at that. And then the states are represented as vectors, which is why we also looked at vectors. And now this question really brings all of that together, which is why I thought this would be a nice question to go through. So the H matrix, or the Hadamard gate operation, is 1 over square root 2 times 1, 1, 1, -1. And then the 0 state is 1, 0. Now, this looks a bit complicated, but this stuff looks a lot more familiar to what we've been going through in the last hour or so. And that's exactly what we're trying to do. This is a matrix, this is a vector, and we're trying to multiply these out. So 1 over root 2 times 1, 1, 1, -1. So this is also known as applying the Hadamard gate to our qubit. Qubit is a quantum bit. So this is our qubit, 0, and we're trying to apply a Hadamard gate to it. And the way we do that mathematically is this. And we're going to see, we're going to do this sort of stuff. We're going to get a computer to do it for us. I think we're going to look at Qiskit, which lets you do all of this cool stuff. So yeah, but it's good to know how the maths works. So again, this is just normal matrix vector multiplication. I think there was a question about multiplying these out, so I think this will be a good example for that as well. So notice the 1 over square root 2 is just a scalar. So that would be 1 over root 2. That doesn't affect it. And the way we do matrix vector multiplication is we take the row and we times it by the column. So it's like an inner product. So if you just forget we had these bottom elements, and if you just looked at like the inner product of 1, 1 and 1, 0, how would we do that? Well, we just do 1 times 1, which is just 1, plus whatever is on the second element, and then the second element. 1 times 0 is 0, so that's just 0. So that just equals 1. And then we do the same thing for the bottom. So we've got 1 and 1, so 1 times 1 is 1. And then plus Again, we've got a 0, so that actually clears things up and that makes it very nice for us. And we get 1 over root 2, 1, 1. This is actually one of the special states. This is also represented as the plus state. And the plus state is an equal superposition, and that's what Hadamard does. The meaning of this is that we have an equal superposition of both states when you apply a Hadamard gate to the qubit 0. And how we'd write this out, how we'd break that down, just so you can see that a little bit better. And it's also given in the question, I believe, is 1 over root 2. And then the 0 plus the 1. So these two statements are equivalent, but for the purposes of the question, that is your final answer. So this is like a lot to take in if you're seeing this for the first time. Are there any questions that I could potentially clarify? Doesn't look like it. So I'm assuming you're all happy with this stuff. So essentially what we did was we did a matrix vector multiplication. So that was our matrix, which was H. That was H. And then we did vector multiplication. And then we've got our final answer. When do you use this operation? Well, you use this operation when you want to put your qubits in an equal superposition. So that's when you'd use this operation. This like the proof that 1, 0 have 50-50. Yes, the recording is available. It will be posted on Canvas. So I'd recommend that you check in a couple of days when it should be made available. So yeah, it's going to be there on Canvas. Hamza, I don't quite understand your question. How do we know this is an equal superposition? Well, we looked at the question where we had to, I think it was, what question was it? Was it 29 or 28 it was, where we had to find the probability of, oh, thank you, Rachel. Just going to post it in the next 24 hours. So it's going to be there for you pretty soon. So we had to find the probability of like one of the states. And the way we did that was we squared the probability amplitude. Remember, this is the probability amplitude. So when we square 1 over root 2, we end up with a half. And so that's how we know that there's a 50% chance that it could be state 0 and a 50% chance that it could be state 1. So I don't know if that quite answers your question, but I think it answers the question that I interpreted it to be. Okay, cool. So that was question 29. Then we've got question 30. So let's see. 30, let's do part D. Yeah, okay, let's do part D. And if you haven't had a chance to go through these questions on your own, I would really recommend kind of working through it, especially the questions in topic 3, which focus on like the quantum stuff, just because I think it's going to be helpful for the semester and it would just really consolidate your knowledge. Yeah, so anyway, this is question 30. So that is the minor state. And this is another superposition state. And that is 1 over root 2, 0, minus 1. And what does the question actually ask us to do? Use the results from the previous question and calculate the following. Right, so this question's quite nice, actually. And because we haven't had a chance, just in the interest of time, to go through every single one of the questions, you're going to have to trust me on some of the things I say. But when you do the homework yourself, you're going to see for yourself why that is. So the first thing that I'm going to do is write out this minor state in this expanded form. So H times 1 over root 2, 0 minus 1. Okay. Now, when you apply a quantum gate, it applies to each of the qubits individually. So this is the same thing as saying 1 over root 2. That's because that's just a scalar. And applying h to 0, which by the way, notice is the exact question that we've done like a couple of minutes ago. And then minus 1 over root 2 of h1. So far, so good. So basically, all we're trying to do is we factor this 1 over 2 out, but we're taking it inside of these brackets, and also we're applying the Hadamard gate to each of the qubits that we have. And this is where you use the results from the previous part, because we know that when you apply h to 0, what did we get like literally 2 minutes ago? It was the plus state. And so that's why it says use the results from the previous part. And this is where you're going to have to trust me a little bit, because when you apply h to 1, you get the minus state. And you can verify that, and I encourage you to verify that, but in the interest of time, I'm just not going to do it here. Right, and again, we know what the plus and minus states are, so we can expand this a little bit further. So we can write that out as 1 over root 2, and then plus state is 1 over root 2 times 0 plus 1, and then take away, yeah, if I put brackets, because we have another 1 over root 2 here as well, so actually, yeah, let me simplify that. Okay, I hope that's legible. Minus, again, we have 0. Look, this is what we're looking at now. And then plus 1. So that's what we have now. So the 0 plus 0 minus 0 kind of go away. And then we have 2 lots of the state 1. So I'll just do it here. So 1 over root 2, first of all, we've got 1 over root 2 times 1 over root 2, which is half. And then we've got 2 lots of the state 1 essentially. So that's that. And then half times the 2 is 1. And that works out to be just 1. So when you apply the Hadamard gate to the minus state, you get 1, which in vector form is 0, 1. So that's how you do these sort of questions. And question 29 and 30 especially, I think, in my opinion, are really good to sort of practice. So yeah, that is that. Okay, you understand now better from this example. That's great. I'm glad to hear it. Are there any other questions at all on this? Doesn't look like there's any questions. So that was all of the main content. Would people like to go through, because now that we're doing like matrices and stuff, would you like to go through like challenge number 2 or 3 maybe even? Or do people have any other questions that like me to walk you through, or any other concepts from any of the maths that we've done so far? Okay, this example helps a lot. Okay, good to know that this is helpful. Oh, Rachel, you flatter me. Am I not an excellent teacher? Well, so yeah, so would people like to go through any of the challenge questions at all? Oh, thank you all. You're being very, very kind. Well, if there's nothing, and if people don't really want to go through any other questions, I think that is it from me. Thank you all very much for coming tonight, and yeah, I wish you good luck on the course, and yeah, I know we're gonna have a good time this semester, so yeah.
Cool. Thank you so much, Nitya, and I will get this recording uploaded to Canvas.
Amazing stuff.
Have a great weekend, everyone, and see you in lecture on Sunday.
Awesome. Thank you so much. Bye.